Hello again, this is James Camp from Lee College in Baytown, Texas, and these are my notes on Chapter 6 of Big C++ by K. Horstmann. We're doing Part 2 of Chapter 6 on two-dimensional arrays and vectors. But first, K. Horstmann has a couple of little sections on problem solving that we're going to go through fairly quickly. First off, we've now seen lots of algorithms for manipulating arrays. This is a very common way to write programs in the real world, is to look up an algorithm that does what you want to do and try to implement that algorithm. This is not cheating because in many ways there's no reason to reinvent an algorithm that's already been worked out for you. On the other hand, quite often the problem you're trying to solve does not exactly fit any algorithm that's already been worked out, or at least not any of the ones that you know or can easily find. So adapting an algorithm is an important skill to learn. So for example, let's say that the final quiz score is the average of your quiz scores in the course you're taking, but the professor is nice and drops the lowest score. You'll need an algorithm to calculate the sum of all the quiz grades, but you'll also need an algorithm to find the minimum value, and assuming you want to remove that element from the list completely, you need our algorithm for removing an element from an array. The problem is that the algorithm we know for removing an element from the array removes by knowing the position of the element, but the algorithm we know for finding the smallest value simply finds the value, not the index. So we can adapt another algorithm that does find the position. We know an algorithm for finding the position of a value we want to know. Well, we can adapt that algorithm. Instead of the if values at position equals 100, we can change it to if values at I is less than values at a current smallest position. Okay, so this time we kind of merge those two algorithms, and instead of tracking the smallest value, we track the position of the smallest value. So we initially set the smallest position to 0 because we don't know any better, and 0 is a good guess. You know, the first position is a good guess. Then we start with I equals 1 because there's no reason to check 0. And if values at 1 is less than values at 0, which is our smallest position, then we'll set smallest position equal to 1. And then we let I increment to 2, and we repeat that. And pretty soon we've gone through the whole array, and smallest position represents the I value at which we found the smallest value. So that adapted algorithm gives us this four-step process. You find the position of the minimum, you remove it from the array, you calculate the sum, which now would be without the lowest score, and then you calculate the final score, which would be the average. There's another way if you don't want to actually delete data from your list of grades, which I find kind of troublesome. You can find the minimum value using that algorithm that we already have that finds the minimum value, and just store it as a little variable called smallest. Then you calculate the sum, but you subtract smallest. And then when you calculate the final average, you also subtract 1 from the number of scores you're dividing by, and that gets you that's another way to adapt several algorithms that you already know. Okay, what if, on the other hand, there is an algorithm you're trying to discover, an algorithm you're trying to work out, that you really cannot find an algorithm in your textbook or on the web that does this already. You need to work out the algorithm on your own. One technique when you're working with arrays is manipulating physical objects. So if you want to work out a sorting algorithm, you could have a stack of playing cards that's shuffled and try to see if you can figure out the most efficient way to unshuffle those cards to sort them into order. In this case, the problem we're given is that the first half of the array needs to swap with the second half of the array. Not sure why we'd want to do this, but this is the problem we've been given to solve. We can set up an array of 8 coins that we just pull out of our coin drawer. Everybody has a coin drawer, right? And we can swap the coins in the same way that we'd swap array elements. We just move one out of the array, move the other one to, we just move one out of the array, move the other one into its place, and then move the other one to the new place, to the place occupied by the former one, and now we've swapped those two places. One way to solve this algorithm, and this is by far not the only way to solve this, is that we find that if you swap the first and fifth coins, and then the second and sixth, and then the third and the seventh, and then the fourth and the eighth, you will end up having swapped the first half of the array with the second half of the array, one coin at a time. This is a pretty efficient method because you're working in parallel. You're working through the array in a logical order, so that you'll notice that the coins we're swapping are always 4 coins apart. So that means that we're moving through the array in a logical order. Now let's look at this a little bit closer. When we swap the first and fifth coins, the first is going to be position 0 in an array. The fifth is going to be position 4, which we can decide is 8, the size of our array, divided by 2. Okay, so we start with, the first index we want to use is, we'll call it I, is going to be 0, and the second index is going to be size over 2. When we move to the second and sixth position, we're looking at position 1, which is I plus 1, and position 5, which is j plus 1. So all we have to do after each swap is plus the array index. And we keep doing that how long? Until we reach, until we've gone halfway through the array. So until I is no longer less than size over 2. So there's our pseudocode. We start with I is 0, j is size over 2. While a is less than size over 2, we swap the elements at positions I and j, and then we plus I and we plus j. Okay, translating to C++ from this point is relatively simple. Most of those lines of pseudocode that I just gave you translate directly into C++ commands, and in fact there's even a swap function in the algorithms header that will swap the elements for you. So you really could just literally translate this line by line into a C++ program. Okay, now let's get back into learning C++ syntax as we explore the idea of 2D arrays. It often happens that you want to store values that make up a table of some sort, okay? Rows and columns of values. So instead of, so far the arrays we've been dealing with are a linear collection of values here, okay, at positions 0, 1, 2, 3, 4, 5, and 6 in this case. But what if we had a second dimension to our data and we wanted to store data that made up a table of some sort. This might be sales figures broken up by sales division on one side and month or quarter on the other. It might be scientific data gathered from a grid of different, it might be literally geographic data where one dimension is longitude and the other is latitude. There are a number of ways you could, situations where you might find yourself working with two-dimensional data. Okay, one simple, if a little bit silly example that he uses is Olympic medals. Okay, we know we have three kinds of medals: gold, silver, and bronze, and we have, say, in this case, 8 countries that competed in the Olympic skating competition that won at least one medal. So what we want to do is store gold, silver, bronze along one dimension and the number of the country. So we'd call this, gold would be 0, silver would be 1, bronze would be 2. Okay, and then Canada would be country 0, Italy would be country 1, Germany would be country 2, and so forth on down the line. So we make a two-dimensional array in C++ by using 2 subscripts and brackets to refer to the rows first and the columns second. So if we want 8 countries and 3 medals, we would define our two-dimensional array as counts at rows here, which is 8, by columns here, which is 3. So that gives us 8 rows by 3 columns. We can initialize the array just as we can a 1D array, except that we need to use 2 sets of curly brackets. Each row gets its own set of curly brackets here, with the columns separated by, this is column 0, column 1, column 2, and the columns are separated by commas, and then each row is separated by a comma after the curly braces. So you can check yourself here and try to write a code statement that declares an array called A of integers that has with this 3 rows and 2 columns, 2 rows and 3 columns, and 2 rows and 2 columns where the diagonal, the place where the row and column are the same, gets a 1 and everything else gets a 0. So you can try that on your own. I'm not going to take the time to write out each of those examples here. Okay. Now, how do we access an element in the array? As you might expect, we just put an index in square brackets for the row and then again for the column. So 3 finds us 1, 2, 3, 0, 1, 2, 3. So that points across this way. 1 finds us 0, 1, so that pulls us down this way, and so that is going to capture that element there is counts at 3 sub 1. Okay, and then if we want to set the value, we just put counts at 3 sub 1 equals 8. Okay, what if we want to print the entire array? Well, we just use 2 for loops, exactly the same style of for loop that we've been using so far. I, of course, begins at 0. I is less than the number of rows. Okay, then for the ith row, we get j starts at 0, j is less than the number of columns, and then for the jth column in the ith row, we're going to see out. This is where your set width operator comes in real handy, to make sure that we space out our columns. Then we're just going to print counts at I sub j. And then you need to remember to always, after you finish a particular row, see out an end line so that you start a new line, and you don't just print all of them in one long row of text on the screen. What this array doesn't do is print your column headings. What this code doesn't do is print your column headings. So you'd really want to have one more C outline up here that prints gold, silver, bronze, so that you know what those different columns mean when you look at them on the screen. Okay, as before, columns and rows are both 0 indexed, so our rows go from 0 to metals -1. Our columns go from 0 to countries -1. Let's say we wanted to sum the total of silver metals. We can make a constant silver equals 1 to refer to which column we're summing up. Then we start with our total equals 0, and then we do a standard for loop, I equals 0, I less than countries, I plus plus. That's going to count all the rows from 0 to less than countries. That's going to count all of our rows. And then the total picks up counts at I sub silver. So we're always going to look at the silver column to get the total of silver metals. We can do the same the other way around. We can make a constant USA, which we know is country number 7. It's row 7. So this time we count up the columns. We go J equals 0 to less than number of metals, and at each point total gets the value, counts at column USA, row USA, column J. So we're always looking at row USA, and we're changing the column. Okay, now if you need to pass a two-dimensional array to a function, it gets more complicated. You have to tell the function how many columns the array is going to have, and you have to do that at compile time, not at runtime, because when you look at an array in a computer, what you've really got is a long list of memory boxes that are just partitioned one after the other. And there's nothing marking where a new row starts. So if we have, in this case, 3 columns, then you have to tell the computer that 1, 2, 3, here's a new row, 1, 2, 3, here's a new row, 1, 2, 3, here's a new row, and so forth. Okay. And then once you've done that, you can refer to your, you can go back to referring to your indexes by row and then by column. And so if row is 2, then C++ would know to skip row 0, row 1, and go to row 2, and then look for 2, 0, 2, 1, 2, 2. Okay. That function will only ever work for arrays of 3 columns. If you also have a 2-dimensional array with 4 columns, you'll actually have to write a different function that has 4 as the number of columns. Okay. Now, when we did that, the row total function didn't need to know the number of rows in the array because we were only ever going to use 1 row. But if we want to do a column total, we need to tell the array how many rows the array has. And we do that the same way we've always been doing it for passing arrays to a function. We just add a parameter that tells it how many rows the table has. And then you would tell it which column you want to sum up, and it would skip around from row to row looking for column. Maybe column is 1, so we'd go to the column 1 in each row in the table. Okay. So this is a practice moment. This function should return the result of adding the values in the first row of the 2D array. So we're always looking at the first row. So k is 0 to columns. Okay, k is 0, k less than columns. So k is going to be our second index in the array, and we're always using the first row. So we're going to sum is sum plus array at 0 sub k. Okay. You may want to stop the presentation here and go take a moment to do the 2D array practice problem that I've assigned for this lecture. Okay. Arrays have a problem. The size of an array cannot be changed after it is created, and it is created at compile time, not at runtime. So you have to get the size right when you're defining the array in code. Okay. In other words, the compiler has to know the size to build the array. And when you pass it to a function, the function has no way of knowing what size the compiler had set for that array, so you have to tell it about the number of elements that you're using and possibly also the capacity that you built the array at. No array can ever hold more than its initial capacity, or you get overflow problems. So there are a number of reasons why arrays are not always the best choice. Fortunately, every object-oriented programming language in the C family, C++, Java, C Sharp, all of those give us a alternative to arrays that are adjustable size arrays. In C++, these adjustable size arrays are called vectors. Okay. Like the string type, a vector is an object, okay, which means it combines built-in member functions with a place to store data. Because they have built-in member functions that manage the size of the array for you, a vector is not fixed in size when it's created, and you can keep putting things into it pretty much until your computer runs out of RAM, if that's an issue. Because it's an object, we declare it differently. There's not a special syntax like there is for an array where you just define the type and then the name and then you put brackets. Instead, we use what's called template syntax, which means the vector is actually a template for an object that can hold any type of data. It can hold a string, it can hold a car, it can hold a double or an int or a bool, but you have to tell it when you create the vector what kind of data it's going to hold. So you can create a vector of doubles called, say, grades, a vector of ints called counts, a vector of strings called team names. If you define your own data type, which we'll get to after the midterm, you can create a vector of those. Now, by default, a vector is empty when it's created. That means it has size 0, and there are no elements in the vector. You can specify an initial size if you want to populate the vector, if you want to use the vector the way you would use a predefined array. Okay, so you could say vector of double data and then parens 10 to make it initial size 10. Here are some examples. You can have a vector of size 10 that contains ints. You can have a vector of size 3 that contains strings. Now note that these are initial sizes. They do not fix the size of the array forever, of the vector, sorry. They do not fix the size of the vector forever. You can start with a vector of 3 names, but then add 3 more to it if you want, or 10 more to it. You can create a vector of double with no parentheses, meaning it starts with size 0. You can't have parentheses that are empty. Okay, that doesn't work. You can add to the end of an array with the pushback function. We'll talk to that in a minute. You can print out what's already in the array, or you can set things, set values of the array. I keep calling it an array, vector. You can visit everything in the vector the same way you can in a array, except that the vector actually knows its own size, so you don't have to have a separate variable keeping track of the size of your vector. And finally, you can use the same initialization sequence or syntax that you use with arrays with a vector. If you want to start it with a list of values, you can say vector int numbers equals and put your list of initialization values in curly brackets. You can access the elements in a vector the same way as in an array using a square bracket index. So if I create vector of double values and make it size 4, I can display the 4th element by saying cout values at 3. Now that'll print a 0 because I haven't put anything in values at 3 yet. C++ will throw a runtime error if you attempt to access an element that's not in a vector. So you don't want to do that. If we made it size 4 and then we tried to display values at 4, remember that would be the 5th element. There isn't a 5th element. That's an error. Okay. The function pushback adds a new value to the end of a vector. Now this is using language from a different data structure called a stack. You push things onto a stack and you pop them off of a stack. So we're saying we're going to push a value onto the back of our vector, and then if we want to remove it, we can pop it back off and assign that value to a result. You can use pop back without assigning the value to a result, but then you just lose the value forever. It removes the value. When you push back, the vector increases its size by 1. When you pop back, the vector decreases its size by 1. The actual size that it stores in memory doesn't change at this point. What happens is the vector, when it's created, stores some extra memory space and stores a size that's smaller than that memory space. And as you add to the vector, it increases its size variable until it runs out of room, at which point it will create more memory space to store more values in. Okay, so this just shows the effect of pushback 54, pushback 32 adds this value here, pushback 54 adds this here, pushback 37.5 adds another value, the size is now 3, popback pulls off the 37.5 and the size is now 2. You can use pushback to put user input into a vector, so we can dramatically simplify our input loop that we used with the arrays to use a vector. All we have to do is say while we get legitimate input, we push the input onto the back of our vector, and the vector will just keep increasing its size as we add input, so we're never going to run out of room in the vector. With arrays, you had to keep track of the current size and the capacity. Here, the programmer has done kind of a bit of bad style and just hard-coded the size of the array into the program instead of making it a variable, or a constant rather. But they're going to assume that the array values has 10 spaces in it. With a vector, you can call the dot size member function. Okay. If values is your vector, you can call values dot size, and you know that you will always, if you make your for loop go to I less than values dot size, you're never going to exceed the bounds of your vector. That means you can pass a vector to a function without having to also pass its size, because the function can ask values what its size is and use that to sum up the vector. Note that a vector is passed by value. That means the entire object is copied into the function. That can be a tremendous waste of memory if you are dealing with very large vectors, if you're dealing with very large amounts of data. In that case, it's helpful to put the little ampersand there and pass it by reference so that you're not copying huge amounts of memory every time you call a function. You can also use the ampersand to allow you to change the values in the vector. This lets you multiply the entire vector by a constant factor. And if you want to pass a vector and make sure that it doesn't get changed, you can add the constant keyword, which will signal the compiler that you don't want it to change any of the values in values here, and the compiler will warn you if that's going on. Unlike arrays, you can return a vector. You can actually build a vector of, say, the first n perfect squares, and you create a vector called result in the function. You build that vector with pushbacks every time you find a perfect square, and then you simply return the vector, and you specify the return type of that function as a vector of int. You can copy a vector. So if you say vector of int squares and you create all the perfect squares in it, and then you say lucky numbers equals squares, you can actually copy the vector as an object. You can create a second vector and selectively copy from the first vector into the second vector. So if we want to find every value in a vector that's greater than 100 here, we're going to go through the entire vector values, and every time values at I is greater than match, we're going to push that value onto the back of our matches array or vector. You can also remove values from a vector the way we've been removing unordered elements. There's actually a remove member function, I believe, that removes I know there's an insert member function that inserts a value at a certain position. I don't remember if there's a remove one. But they're not going to tell you about those functions here. All the functions in the algorithm library that we've learned about that work with arrays also work with vectors. You just pass them in a different syntax. You use the .begin member function and the .end member function to signal the starting and ending points, and then will sort your vector for you. There are also copy, fill, and min element and max element that will work with vectors. Okay, what if you want a two-dimensional vector? There is no such thing as a 2D vector. What you can do is store a vector of vectors. This gets fairly complicated, and I'm going to leave this to the interested student to try to figure out, because really in this case it's better, if you have a two-dimensional set of data, it's better to work with a two-dimensional array than to try to figure out the vector sizes. The only difference, the advantage of over 2D arrays is vector row and column sizes don't have to be defined at compile time. And if you pass them to a function, you can just pass it as a single variable instead of having to define the column size. So finally, in summary, which to use, a vector or an array? For most of your programming tasks, vectors will be easier to work with than arrays because vectors can grow and shrink. They remember their size, and they have handy functions like begin, end, pushback, popback, size. And there's an at function, which actually includes bounds checking, that will return, that will gracefully throw an error if you detect an invalid subscript instead of crashing your program. Advanced programmers may prefer arrays for efficiency. If you're working in an Arduino microcontroller, for example, where it's very important that you are efficient with memory and efficient with processor time, the array is going to be a better option. I'm not sure Arduino actually even has a vector as part of its C language. And you still need to use arrays if you work with older programs or use standard C, that is without the plus. And again, microcontroller applications like working with an Arduino might not even have the C++ library vector in them. Okay. And I should also mention that standard C is still one of the preferred ways of programming in the Unix operating system. And if you take an operating systems course at, say, University of Houston Clear Lake, if you transfer there, they will require that you write some of your code in standard C. So you'll need to remember all of this array stuff. You can't get lazy and use vectors. And then the C++ range-based for loop works with vectors as well. You can do for int v colon values, and then v will get each value from values will be copied to v one at a time as you go through values. If you want to be able to change the original array, you put an ampersand after your int and make it a copy by reference. The range-based for loop also works for arrays. We've seen that earlier in the part 1 lecture, but I just want to show it to you again. And you can also use auto to automatically assign the type of P based on whatever primes is. So compiler knows that primes is an int, so it would make P an integer automatically. Okay, that concludes part 2 of this chapter. Now is a good time to go do the vector practice assignment that I gave you for this week's programming assignment. This concludes the first half of the course. We'll get into data structures and objects and other advanced C++ tricks in the second half of the course. See you then.